Hello everyone, and welcome back to another video. Today we have a fun little integral I found on Math Stack Exchange, as one does when scrolling through it while I'm bored. And before actually evaluating this, the method we're going to be using relies on expressing inverse tangent as a power series. But before instead of just assuming that we know the series for inverse tangent, I would like to derive it first. So let's do that real quick, shall we? So what we're going to say is that, well, we have this inverse tangent function here. We don't know its power series, but what if we differentiate it? The derivative of inverse tangent, we know quite clearly, is just 1 plus x squared. Or 1 over 1 plus x squared, pardon me. At least I wrote it right. And one thing we also might note is that this 1 over x squared, if we say, well, x is less than 1, or the absolute value of x is less than 1, we can just evaluate this right there as a power series. Because we know if we have 1 over 1 minus x, this right here, again, holding that as true, this right there is just equal to the sum from k equals 0 to infinity of x to the k. So if we just sub in basically an x, or really just make this this x into a minus x squared, this doesn't change this condition right here, and also this is going to be equally valid for the x being a minus x squared. So really, subbing that in, what we find is that the derivative of inverse tangent is just equal to the sum from k equals 0 to infinity of negative 1 to the k, just by properties of exponents, times x to the 2k. And what we found is the series for 1 over x squared, but what we wanted originally was a series for inverse tangent itself. So what we might do is look at this series right here and notice that this x term is really easy to integrate. So what we can do, is the most straightforward thing, and is just go ahead and integrate this function or the series. So let's do that, shall we? What we now have is the integral of this dx. So what we have is inverse tangent of x being equal to the integral of this, and I'm just going to swap the order of the sum and the integral real quick. So we have the sum from k equals 0 to infinity of negative 1 to the k times the integral of x to the 2k dx. And this right here is really simple to evaluate. After all, it is just going to be power rule. So this is just equal to 1 over 2k plus 1 times x to the 2k plus 1. I would write plus c, but since inverse tangent of x, that's just 0 at 0. So our c is just going to be equal to 0, so I'm just going to omit it for now. I say for now. I'm just going to omit it, period. But yes, subbing all this in, or really just kind of putting all of our pieces together, we find that the inverse tangent is equal to the sum of negative 1 to the k over 2k plus 1 times x to the 2k plus 1, so long as x is less than 1, or absolute value of x, is less than 1. And now that we've done this, we can kind of go up a tiny bit, and notice that our function inside our inverse tangent, e to the minus x, on our interval from 0 to infinity, that's always going to be in between 0 and 1. You can just kind of prove this if you just throw it into Desmos, but it basically achieves its maximum on this interval at 0 of 1, and then as you take the limit as it goes to infinity, you're just going to get 0. So what we can do, because e to the minus x on this interval is less than 1, or less than or equal to 1, but it's only 1 at a certain point, so it's okay. But basically, because this right here is true, what we can just do is, we can make this x just an e to the minus x, and then we can just integrate. So let's go ahead and do that. What we have then for our integral, which I will call I, is the sum, or I'll put the integral on the outside. The integral from 0 to infinity of our sum, negative 1 to the k, over 2k plus 1, But instead of x to the 2k plus 1, we're going to have an e to the minus x times 2k plus 1. And then dx, of course. And based off of this, or not really based off of, but what we're going to do is what we did before and just switch the order of operations here. Switch the operators around, leaving us with our integral, our integral is equal to the, oh goodness me, I cannot write a sigma today. The sum of -1 to the k over 2k plus 1 times the integral of 0 to infinity of e to the minus x 2k plus 1 dx. And we can evaluate this integral really simply right here because it's just an e to the minus x times something. I mean, you do this in, the first calculus class you take. I hope. So what we have then is we have e to the minus x 2k plus 1, but then divided by 2k plus 1. And evaluate from 0 to infinity. And what this right here is going to be equal to, it's pretty simple. If you take the limit as it goes to infinity, you get 0. You plug in 0. Sorry, that should be a negative. Pardon me. So, again, plugging infinity, it's still going to be 0. But plugging infinity is going to be 0. But if you plug in 0, what you're going to get is just this bit right here. Basically, just ignore the numerator, but make it negative. Negative times a negative is a positive. So we're left with this integral right here is just a 1 over 2k plus 1. Meaning that we have a 2k plus 1 here, 2k plus 1 there. We can simplify this whole summation to something a lot simpler. We can just say this is the sum from k equals 0 to infinity of -1 to the k over 2k plus 1 squared. And this is more or less where we're going to stop because this is the definition of Catalan's constant, denoted by a big capital G. And do note that this is also the Dirichlet beta function evaluated at 2. But yeah, that's what the integral is equal to. It's just equal to Catalan's constant or the Dirichlet beta function of 2. So yeah, I hope you all enjoyed this video with all of the tangents about tangent, or tangents about inverse tangent, I suppose, but either way works, I guess. But yes, thank you all for watching, and I'll see you on the next one. Adios.